Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
So how to develop this criterion in the uniaxial test? Note that the maximum shear stress occurs on the planes oriented at 45 degree with respect to applied stress. This fact and equations are easily verified with the Morse circle as shown in figure. So this is just to reinforce our understanding, not that anything we are finding it new here. Okay, just to plot these ideas into a Morse circle, and we'll get see the visual experience of the maximum shear stress criterion. Okay, so what is that we are seeing? We are now considering the uniaxial deformation, a tensile deformation, whether it could be a cylindrical member or it's a square member. And we are saying that the maximum shear stress occurs on the planes oriented 45 degrees. So this is the square member. So according to this geometry, this is the plane which we are talking about, which is oriented at 45 degrees. So on this plane, the shear stress is tau prime is sigma 1 by 2, which is nothing but tau naught is equal to sigma 1 by 2. Okay. So same thing is plotted here. So since it's a uniaxial tension, so you have only sigma 1, others are 0. And you remember that this is maximum shear. And in the Morse circle, we always plot 2 alpha, if you recall those concepts. So it is exactly 45 degree. So 2 alpha is 45 degree. So here the 2 alpha is 90. So the maximum shear stress tau is here, and then this is the the principal sigma 1. Okay, so this is very nicely we can represent in a Morse circle. That's what I'm showing. So the equation for yielding can thus be written in terms of sigma naught as sigma naught by 2 is equal to max times tau 1, tau 2, and tau 3. Okay. Or you can rewrite in this form. The effective stress is most conveniently defined in this equation so that it equals the uniaxial strength sigma naught at a point of yielding. That is, so we are interested in relating this into simple yield strength in a uniaxial tension. So it can be rewritten like this: sigma s bar is equal to max times tau 1, tau 2, tau 3. Where the subscript S specifies the maximum shear stress criterion. Okay, similarly, similar to what we have seen in the normal fracture criterion, here also the safety factor against yielding is then x equal to sigma naught divided by sigma S bar. It is a subscript. There is a typo here, sigma S bar. So this is a safety. So we will now move on to another criterion called octahedral shear stress criterion. Okay, this is again for ductile materials only, similar to Tresca yield criterion. Like I mentioned in the beginning, there are different yield criterions are proposed, several depending upon the materials and the state of stress and so on. We are looking at some of the important ones and at the same time simple ones which can be related to simple. This criterion can be related to the parameter which you can normally obtain by the simple uniaxial tension test. That's the idea. Okay. See, the other criterion, shear stress yield criterion for ductile material is octahedral shear stress yield criterion. Okay. So what does it say? Another yield criterion often used for ductile metals is the prediction that yielding occurs when the shear stress on the octahedral planes reaches the critical value. Tau h is equal to tau h naught at yielding. So now we have to understand what is this octahedral plane, right? In our crystal system, we will see it in a minute. Where tau h naught is the value of octahedral shear stress tau h necessary to cause yielding. The resulting octahedral shear stress yield criterion, also often called either the von Mises or the distortion energy criterion, represents an alternative to the maximum shear stress criterion. So this is another way of predicting the yield criterion, similar to maximum shear stress criterion or Tresca criterion. So what are these octahedral stresses? The octahedral stresses are a particular set of stress functions which are important in the theory of plasticity. Okay. They are stresses acting on the faces of a 3D octahedron which has the geometric property that the faces of the planes make an equal angles with each of the three principal directions of the stress. So if you assume that in a cube, when we define state of stress in a cube, and then we looked at all three principal directions, right? So if you recall that cube describing the stress, then you can imagine this. For such a geometric body, an angle between the normal to one of the faces and the nearest principal axis is 54 degree 44 minute. And the cosine of this angle is 1 by root 3. This is equivalent to 111 plane in an FCC crystal lattice. Take a simple cube, the 111 plane, which is nothing but an octahedral plane. Okay, so that is what is talked about here. A physical justification for such an approach is follows. What is a physical justification to look at the octahedral stresses in an octahedral plane? What is the physical justification? Since the hydrostatic stress sigma h is observed not to affect yielding, it is logical to find the plane where this occurs as a normal stress and then to use the remaining stress tau h as the failure criterion. So what does it say? We have been now saying that the hydrostatic stress is not going to contribute to the yielding. So in a total stress, so if you recall that we have looked at one particular lectures exclusively, how to separate this hydrostatic component of a stress and a stress deviator, right? So this here exactly we are using that stress deviator. We are talking about nothing but a stress deviator here, which is very useful now. Okay. So another justification is to note that although yielding is caused by the shear stresses, tau max occurs on only two planes in the material, whereas tau h is never very much smaller and occurs on 4 planes. Very important. You have to remember, although yielding is caused by shear stresses, tau max occurs only 2 planes in the material, right? We have 2 planes, if you recall that image what we have just discussed in the previous slides, where tau h is never very much smaller and occurs on 4 other planes. Okay. So tau max is on 2 planes, but tau h is also occurring other 4 planes. So totally we have seen 6 planes, right? So that's what we are talking about here. Okay. So they are not very much smaller. So we have to look at those. Hence, on a statistical basis, tau h has the greater chance of finding a crystal planes that are favorably oriented for a slip, and this may overcome its disadvantage of being slightly smaller than tau max. So the shear stress which is going to cause the slip also depending upon several other factors like orientation of the crystal with respect to axis of loading and so on. We will see those things when we look at the plastic deformation in much more detail. And taking this shear stress for a criterion, why we take shear stress for a criterion to predict the yielding is this is one of the reason, right? So the shear stress on an octahedral plane is tau h is equal to 1 by 3 times square root of sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. So that the failure criterion is tau h naught is equal to 1 by 3 times square root of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square at yielding. Okay. As was done for the maximum shear stress criterion, it is useful to express the critical value in terms of yield strength from a tensile tension test or tensile test. Substitution of the uniaxial stress state with the sigma 1 is equal to sigma naught and sigma 2 is equal to sigma 3 is equal to 0 into the octahedral shear criterion gives tau h naught is equal to square root by 3 times sigma naught. Okay, so we got now an expression for the octahedral shear stress. From this three-dimensional geometry of the octahedral planes, it can be shown that the plane on which the uniaxial stress acts is related to octahedral plane by a rotation through an angle alpha of the figure what we have seen here below, where alpha is cos to the power minus 1 times 1 by square root 3, which is nothing but 54.7 degree. Okay, so this is an angle with which it is oriented with respect to tensile axis. So again, we will plug in all these values into the Mohr circle. The same result can also be obtained from Mohr circle by noting that in uniaxial tension, the normal stress on the octahedral plane is nothing but sigma 1 by 3. Okay. Locating the point that sacrifice this on Mohr circle leads to a aforementioned values of alpha and tau h naught. How do we do that? So this is again uniaxial tension. This is on cylindrical member. This is square member. We are looking at alpha is equal to 54.7. That is a orientation of this plane with respect to sigma 1, and sigma h is equal to sigma 1 by 3, and tau h is equal to square root 2 divided by 3 times sigma 1. This is what the yield criterion shows. And if you look at the Mohr circle, what is shown here? So this is uniaxial tension, so it is sigma 1 here, and this is 2 alpha. That means it is about 108 something, right? It is 2 times the 54.7 degree. So that is shown here. So this is where the maximum shear stress will lie here, and that is if you look at the corresponding sigma 1, it is sigma 1 by 3, and this is the tau max here, or tau h. The value of tau h is this value, and this is the sigma 1 value. So this is now very easy when you, this Mohr circle concept comes very handy to visualize the maximum stress, normal stress versus shear stress values. So this is for the octahedral shear stress criterion. So the yield criterion in the desired form expressed in terms of uniaxial yield strength is sigma naught is equal to 1 by square root 2 times square root of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square at yielding. Okay. We are interested in to express this criterion in terms of yield strength. That's why we are writing it here. Again, we will now arrive at a safety factor. So we are interested in the effective stress for this theory is most conveniently defined so that it equals the uniaxial strength sigma naught at the point of yielding. So sigma h bar times this same expression here, and the subscript h specifies that the effective stress is determined by the octahedral shear stress criterion, also the corresponding safety factor x equal to sigma naught divided by sigma h bar. So similar to the previous cases, this effective stress may also be determined directly for any state of stress without the necessity of first determining the principal stresses. Yeah, so the result is sigma h bar is equal to 1 by square root 2 times sigma x minus sigma y whole square plus sigma y minus sigma z whole square and sigma z minus sigma x whole square plus 6 times tau x y square plus tau y z square plus tau z square. So what is this expression? If you recall, when we opened up the strain matrix, we looked at all the invariants, stress invariants and strain invariants. If you recall our old derivation, if you go back to our old derivation, J1, J2, J3, these are the three invariants we derived. If you look at the J2, okay, so that it is nothing, this expression is nothing but the J2 invariant, right? So instead of doing this, we can also determine this sigma h bar by directly substituting into this equation. That is why this statement is given. This effective stress may also be determined directly for any state of stress using this expression. So just to give an idea, why we looked at the earlier expressions and how it is useful here now to predict the yield criterion. That's why it is shown here. Okay, now come to the most important idea. We have now created the surfaces, the yield surfaces or yield, or fracture surfaces. Here it is yield surfaces for biaxial loading. This is a Tresca yield criterion, and which shows that 4 quadrants 1, 2, 3, 4, and then you have sigma 1 and sigma 2, and the boundary demarcates no yielding and then yielding. Okay. Stress combinations lying within the solid lines do not result in plastic flow. Those without it do. So that means within this solid line, the combination of stresses sigma 1 and sigma 2 will not cause yielding as per the Tresca yield criterion. Okay. In quadrants 1 and 3, yielding occurs when the magnitude of the algebraically largest in 1 and smallest in 3, right, exceeds sigma y, the tensile yield strength. Okay, so this is quite obvious from looking at this. Okay. In quadrant 2, on the other hand, sigma 2 is greater than 0 and sigma 1 is less than 0 and sigma 3 is equal to 0. Yielding is defined by sigma max, that is nothing but sigma 2 minus sigma minimum, that is sigma 1, is equal to yield strength. So sigma max minus sigma minimum is equal to yield strength, and this results in the 45-degree line defining the yielding. Okay, so this is what it is shown here, 45-degree line here. And in the yield criterion is similar in quadrant 4, except that it is just reversed here. So sigma 1 is greater than 0 and sigma 2 is less than 0 and sigma 3 is 0. Okay, so that is what's shown here. So what is this image now shows? It is showing the same yield criterion here, but also it plotted the von Mises yield criterion, which is a solid line again, this over this. This is again the von Mises yield condition for biaxial loading, is shown by the solid line. What you can see is the Tresca is the more conservative criterion, and the two criteria are equivalent only for uniaxial, that is sigma 1 or sigma 2 is greater than 0, with sigma 2 and sigma 1 equal to sigma 3 is equal to 0. And balanced biaxial, sigma 1 is equal to sigma 2 and sigma 3 is equal to 0 loading. So only it is uniaxial and balanced biaxial loading. These two criterions are equivalent. Otherwise, the von Mises yield criterion shows slight deviation when you move away from the principal axis, right? So this particular image, it shows the experimental findings. You can see that it's quite interesting. These are the experimental data obtained for steel, copper, and nickel, and then you see that most of the data points lies just close to von Mises criterion, but not very different from Tresca, but then it is close to von Mises criterion for a biaxial loading. Okay, now we have to turn our attention to yield criteria for other than crystalline materials or semi-crystalline materials called polymers, right? So far, all this yield criterion represented the failures of or yielding of crystalline material or ductile materials or even a brittle materials, where we looked at the maximum normal principal stress or fracture stress criterion, right? So those things, those yield criteria will not work for polymers or semi-crystalline or amorphous material. So we look at it. What is the change required to predict the yield criteria for polymers? So it has been seen that polymers typically have very different yield behavior in tension and in compression, and this can be attributed to hydrostatic pressure effects. So if you recall, when we looked at elastic properties in the earlier lectures, we have clearly shown how this semi-crystalline materials or long chain molecular materials, how they behave in tension as well as compression. Very nice illustration we had. We had also discussion about how this compression behavior is entirely different from the tensile behavior when it comes to deformation of long chain molecular materials, or namely polymers, right? So that is exactly is brought here. So the hydrostatic pressure effects, okay, has to be taken into account. First, it is seen that yield in tension occurs at lower true stress than the yield in compression. This also we have seen. Okay, the slope of the stress strain curve, even in elastic region, in tension and compression for this long molecular chain molecular materials, they are not same. They are very different. Okay, since we have already seen this, I am just going little fast. So that is the purpose we spent some time on the fundamentals, right? So you can easily recollect, and even if you have doubts, you can go back to those sections and then read them. Then it will be easy. As positive pressure, that is compressive stress, is exerted on this low stiffness material, the chains are pressed together and the chain mobility is diminished. Okay. Conversely, under the negative pressure, that is tension stress, the average spacing between the chains in the direction direction perpendicular to the principal normal stress is increased, and the chain mobility is enhanced. This point also we have already seen. So in the light of the significant influence of pressure on polymer yielding, several pressure-dependent yield criteria have been proposed and compared to the experimental results. So one thing is very clear. We are going to look at the yield criterion, almost similar kind, but the one parameter which is very new here is the pressure effect. Okay. So the Mohr-Coulomb model, which is going to describe this, and the modified Tresca criterion, so are based on the existence of a critical shear stress, just like the classical Tresca criterion. We are going to use the same criterion like what we have seen for ductile materials. We will simply use the pressure effect on them, and which is called Mohr-Coulomb model. Okay. In the Mohr-Coulomb model, the pressure influence is described as a simple normal stress imposed on the plane of sliding with a frictional term added to couple the normal stress to the critical shear stress. Very important. Okay. So this model brings the pressure influence where the normal stress is imposed on a plane of sliding. So we are talking about now molecular chain which are sliding. It is sliding of this molecule chain with the frictional term added to couple the normal stress to the critical shear stress. So it takes the form tau mc. Mc is Mohr-Coulomb model is equal to tau c, critical shear stress, minus mu mc sigma n, where mu mc is the critical shear stress in the presence of normal stress, and tau c is the critical shear stress in the absence of normal stress. Mu mc is the coefficient of friction, and sigma n is the normal stress, negative for compression as written. Okay. So this is a significant departure from the case of metals and ceramics, for which the normal stress plays no role in determining the yield. So very important idea. Okay. Where we are bringing a normal stress into an yield criterion. Okay. Especially a Tresca yield criterion. So what is that we have seen so far in Tresca? So this is what this plot shows clearly. This is normal Tresca yield threshold is shown in a dotted line here, a thick dotted line, and this is tau, and this is sigma n, and we have now put another slanting line which is having an angle with respect to this horizontal line phi, and that we call it as pressure modified Tresca. Okay. So the Mohr-Coulomb criterion is also sometimes written as tau mc is equal to tau c minus tan phi times sigma n, where phi is the angle that the yield surface makes with the classical failure surface as shown in the figure. Okay. Note that the Mohr-Coulomb criterion does not distinguish between yielding under the uniaxial or multi-axial loading. Okay, this is one limitation. The pressure modified Tresca criterion, however, treats the pressure phenomenon in 3 dimensions, but it has the similar form. So tau t is equal to tau t naught plus mu t times p, which is also written as half times sigma max minus sigma minimum is equal to tau t naught plus mu t times p. Okay, where mu t is the pressure coefficient and p is the mean hydrostatic pressure. That is, p is equal to 1 by 3 sigma 1 plus sigma 2 plus sigma 3. So that p is positive for hydrostatic compression. So what you now see is here we are using the similar Tresca criterion where the pressure effect is very nicely brought in, to accommodate the polymeric or long chain molecular behavior under compression. Okay. The pressure modified version of von Mises criterion, yield criterion, depends upon the critical distortion energy, just like the classical version, and takes essentially the same overall form as the modified Tisca, which is tau Vm is equal to tau oct 0 plus mu Vm times P. So this is von Mises yield criterion. So tau Vm is the critical octahedral shear stress for yielding as a function of pressure. Mu Vm is the pressure coefficient and P is the mean pressure. Here tau octa naught is the critical octahedral shear stress determined in the absence of hydrostatic pressure. Okay. Note that for uniaxial loading, tau octahedral is equal to square root of 2 by 3 times mod sigma, where P is equal to minus sigma by 3. All the pressure modified yield criteria assume a linear dependence on the pressure. This is one thing we have to note. It has been found that this works well at low pressures, that is 100 MPa, but may not be suitable for very high hydrostatic pressures. So for that, some other empirical models have to be looked at. So with that, I would like to stop here. We will continue our lectures in the next class.